In this video we're going to cover the multiplexing for the rounding. So for example, if we drop into the shifter, we have to be able to make the correct choice here through these two multiplexers, whether we're going to pass the rounding bits on with no change, or whether there's going to be a right shift or a left shift. And you can see we've got the multiplexer control bits, so that's this little circuit here. So we're going to get that from the normalized section. So you can see here that we've got this MR times 2 and MR divided by 2. So this really MR times 2 is the left shift of the mantissa. The MR divided by 2 is the right shift of the mantissa. And these are the inputs, and we get them from the normalization. And these are the two outputs from the normalization here. So let's go ahead and we'll drop in there and we'll see where we get them. So you can see here that we've got this extra section here added, which is rounding, and we've got the circuit here which will provide us our MR times 2, and we've got a circuit here that will provide us with the MR divided by 2. So let's go ahead and we'll see where we got these circuits. Now we were able to work out these circuits from our original truth table for our addition and the truth table for our subtraction, and we've got an extra truth table here as well in order to choose the value for the MR going straight through without any change. So there's several different ways of doing this, but I just worked through the truth table to get something that would work quickly, and it's obviously it's maybe not the best option or the simplest option, but it does work. So if you were to say, for example, we took our SZ here, and we've seen that if the SZ is value of 0 and the bit 25 is a value of 1, then it doesn't care. We don't care about bit 24. It's 0 or 1, so it's really I don't care for this. Then we're going to have our ripple, that is, we're going to have our exponent plus 1, and it's our mantissa divided by 2. So we're really interested just in the mantissa. So it's going to give us this here. So that means that all we need is a little circuit that's going to take in the value for SZ, and whenever SZ goes high in bit 25, when SZ is low and bit 25 is high, then we know we're going to have our MR divided by 2. So we could quite simply just put the SZ in, and we could put it through a little inverter, and then we could put the value for bit 25, and we could pop that through a little AND gate, and that would head out to the output. So this is going to be bit 25, and this is going to be our SZ, and then we're going to have our output. So this is going to give us our MR divided by 2. So quite a simple little circuit. Now we can do the same for the MR times 2. Now the MR times 2, we're going to have this value here, and we're going to have this value here. And we're also going to have bit 24, which is going to be it's actually this value here, so I'll undo that just now. So it's this value here for MR divided by 2, and this value here for MR divided by 2. And you can see here in this instance here that we choose bit 24 in this instance. So you can see that if the sign of Z is 1 and bit 24 is a 0, then we can see that in these instances it would be a 0 for bit 25 and a 1 for bit 25. So we don't really care about bit 25, it just changes and we don't really care. So it means that we can draw out for this little circuit here in order to get the MR times 2. We can have SZ is going to be high, so we can just put SZ in, and the value for S for bit 24 would be low, so we could put bit 24 through a little inverter and then pop that through an AND gate and take the output here, and we would have the SZ here, we would have our bit 24, and then we would have our MR times 2. So these are our two little circuits that we can get in order to make the choice of the MR times 2 and the MR divided by 2. Now there's one other option that we need to cover, and that is when there is no change. That is, we want to just have an MR. So again, with two multiplexers, so we have to have the two values coming in for the controls. So what we could do is we could just create a little truth table for these MRs. So we have our MR times 2, MR divided by 2, and the MR. So in this case here, we could say that if we have a 0 for MR times 2 and a 1 for MR divided by 2, then we could call that MR times 2. And this one here, we could call that MR divided by 2. Now, these other two options here, 0, 0 and 1, 1, well, 0, 0 and 1, 1 don't occur because the MR times 2 and MR divided by 2 are both mutually exclusive. That is, we won't get one and both of these occurring at the same time. So if that's the case, then we can really just make these don't care states, in which case we could just call this don't care state, we could just call this the actual MR. So the actual MR here means no change. So we would have a no change for these ones, and then we would have MR times 2 for this, and MR divided by 2 for this. So it means that we only need to pass on these two options here, MR times 2 and MR divided by 2. So let's go ahead and we'll see these circuits inside our Logisim. So let's head in to the normalized section here. And you can see here that we've got the two little circuits that we talked through. We've got our addition with a ripple, which gives us our MR divided by 2, which is this circuit, and our subtraction with the cancellation, which is MR times 2, which is this little circuit here. So let's head up and we'll see these in the shifter. So you can see here we've got our MR times 2, MR divided by 2, and these come up into the circuit up here. So now, in order to give us the final control bits for our multiplexers, we're going to have to cover the final truth table. So the final truth table was this little truth table here. So if there was a 1, 1 or a 0, 0, then it's just going to cover the no change, which is just the MR just passes through. And then with the 0, 1 is MR times 2, and the 1, 0 is MR divided by 2. So we've got our no change here, which is we bring in our MR times 2, MR divided by 2. If we put them through, both of them through NOT gates, then we're going to have the values 0, 0 and 1, 1 are going to occur, which will control the passage of the no change round bit. And these other two here are going to cover the MR times 2 and the MR divided by 2. So finally, once the choices have been made, we're going to take out the guard bit, which is the 24th bit, and we're also going to take out the other 23 sticky bits, and those are the outputs here, the guard and the sticky. So that covers everything that we need to cover within this block here. Now there's just one other thing we need to talk about, and that is down in this section here. When we've seen here we did the subtraction with the cancellation, then we know we're going to have MR times 2. So if that's the case, then instead of passing out just the value here for MR, we're going to be passing out the value for our MR, which has been shifted and it's had the guard bit injected. So we need to make a choice between these two. And again, we make the choice between these two dependent on whether we have had the subtraction with cancellation. But we've already worked that out here. If we have the subtraction with cancellation, we can just use this little circuit, and which is MR times 2. So we just control that with the MR times 2. So you'll note that previously the output for our mantissa was this value here. But now we've had to break into this point because we have to choose whether to pass this value out for the mantissa or pass this value for the mantissa here. Now the value for the mantissa here is the value that we get whenever we do the subtraction with cancellation. So that is, we've had to inject the guard bit. So we need to make a choice between these two. And we make the choice between these two with the MR times 2. So we've already built that circuit that tells us whether we've had a subtraction with cancellation, in which case it's going to choose this value for our MR out and not this one. Now finally we take that MR out and we put it in through an extender and we get rid of the hidden bit. Now in the next video we'll cover the actual rounding section here, which is just a simple realisation of the truth table which we talked about in a previous video. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.